Very good. So now let's try to take all of these consequences here of relativity and see what happens when we begin to have charges moving. So here's the example I would like for us to consider then. Here, move this all the way up here, a nice clean slate. I want you to imagine that we're going to have then a typical situation where we have moving charges, some current carrying wires. So let's consider then two parallel wires carrying a current. And they might both be carrying the same current, I, right? Now we know, microscopically what this means. Here I'm going to try to sketch them for you. So here's one of my wires. I'm going to be very explicit here about physically what's happening, right? Inside the wire, I'm going to have, let's see, how am I going to do this here? I'm going to have, some positive charges, of course. And if this is a metal wire, these represent, the nuclei, right? They're going to be stationary in my wire. These guys are not going to be moving at all. There are, though, of course, electrons in my wire. And those electrons will be moving. And in here, my example, I'm going to imagine that these electrons here are all moving along. Here, I'll pick one of them, right? He's moving along to the right. All of them are, in fact, moving along to the right with some drift velocity v sub d, right? And I'm going to be, say, here, standing here in the laboratory, observing this. Of course, I've only drawn one wire so far. We'll look at the other wire here in just a moment. But we know, of course, when the negative charges are traveling this way, it must mean that what I've done is I've decided to pump a current I, right, down the wire in that direction, because the electrons traveling to the right is equivalent to our standard current, which we consider to be positive charges moving off to the left. But in our example here, we'll actually have the standard case of the electrons carrying the current. So that's what's going on in one of my wires. I'm going to have another wire, a second wire. It's going to be the identical situation to make our analysis a little bit easier, right? So there's going to be, again, all of these stationary positive charges. I'm only drawing one row of them. Of course, there'd be many rows, many atoms in there. Then I have these minus charges here again, like so. And these guys also, because these will be identical wires, they will be carrying identical currents. Everything's identical. So all of these electrons here also will all be moving off to the right with some drift velocity Vd. Okay? So that's what is going on then in the laboratory. I want to think carefully now about relativity and what things look like here with these current carrying wires, what they look like, in fact, to some of the moving charges. So I'm going to pick out, say, this one moving charge up top, and I'm going to focus on what his view then of the situation is going to become. So I'm going to draw this very carefully. So that was the original situation. Now I'm going to draw again here this lab frame, but I'm going to try to be very careful here exactly how I draw it, because I'm going to compare now the lab to the reference frame of the electron. So in the lab frame again, what I have is I'm going to just redraw my lower wire here, right? So in the lab, and then pick out just this one electron up top. So I have this one electron, so I'll draw him first, right? Moving along this way at velocity Vd, right? And then down below, I have a wire, and we know that this wire, which is carrying my current I, right, has in it a bunch of positive charges, of course. I'll draw them, down on the bottom now, just so I can focus on the minus charges. But I've got all these positive charges down here. Fine. And now the wire, of course, when it carries the current I, remains neutral, right? Because charges can flow on there very quickly if there was any imbalance of charge. And as we've said in the past, what I have then again are my minus charges here. And these minus charges all happen to be moving, of course, in the same reference frame here as my moving charge up above that I'm thinking about, right? They're all traveling then with that same specific drift velocity. And so there's going to be, of course, some natural separation between the positive charges. I'll call it D in my wire. And, of course, because the wire remains neutral, the average spacing then between the negative charges all still has to remain D. And the final actor here in the laboratory is my observer, which I will sketch over here like so. So this is the lab frame, and I'm going to actually label it lab, L-A-B. Okay. Now, that's the lab's reference frame. Now, what I had said was I wanted to think relativistically about what the world must look like to this here negative charge, right? In the lab frame, everybody is at the same spacing D, both the positive and negative charges, but we know the situation is going to be different for this traveling negative charge, right? Just like our traveler who was on that spaceship moving off to the right, for instance, one of the first things we can expect, here I'm going to sketch my wire. Here's my wire. And now I'm no longer in the lab frame. I'm in the frame of the moving charge, right? That charge frame. And in his frame, of course, the moving minus charge is just now stationary, just sitting in his chair like Sally was sitting on her rocket ship. And now because that we know that that's like Sally on a rocket ship traveling off this way past a whole series of stationary mile markers, right? We know then that the distance between those mile markers must now be smaller. It must be contracted by this length contraction effect. These are just like, the distances between the stars in our previous example. So this distance between these positive charges is now less. It's equal to D divided by gamma. Remember, gamma is a number more than 1, right? It was like 5 in the Sally example. So this distance here is going to be gamma inverse times D between those positive charges. Now there's another interesting effect that goes on here. As far as the charge is concerned, remember also the person who was standing in the laboratory frame, that person now is moving this way with a velocity v sub d, right? This drift velocity that the charge had, right? The charge, riding on the charge, you see the person coming at you, right, as you move towards the person. So now it's the person that's moving this way. And as far as this minus charge is concerned, notice this person is moving past what are stationary mile markers as far as the minus charge is concerned. Let me back up. That's a little bit tricky to understand. But notice my minus charge in the upper wire that I'm focused on right now is moving along by supposition with the same drift velocity as the minus charges in the other wire. So these minus charges, all of the minus charges, are all traveling with the same speed. They all share the same frame of reference. So there's a whole series of these minus charges, which are now further spaced than the positive charges, but there's a whole series of these along my wire. And as far as the minus charge is concerned, those are stationary. And what this minus charge is observing is that these stationary charges have an observer who's traveling past them. So that observer must be seeing these stationary charges as closer, right, as length contracted, than what I, this minus charge, regard them to be. So the minus charges must be closer together here in the lab frame than they were here. So these are not length contracted, right? These are actually length expanded relative to the previous frame. I know that might be a little tricky to follow, but that is indeed the case, d times gamma. Again, the idea is this. This distance, d times gamma, which is bigger than d, right? Like 5 times bigger if we're traveling near the speed of light. That's bigger than d. It has to be bigger than d in this reference frame because the observer, right, who saw them at distance d is traveling past them as now stationary mile markers. The main conclusion, though, here, no matter how you stack it up, right, is that definitely, even if you don't buy my argument about the minus charges, although I assure you it's correct, certainly the positive charges would be contracted together in this reference frame. So whichever way you care to look at it, the key thing to notice now is that there is a higher density of positive charges on this wire than negative charges. That's very important, right? The lambda, the charge density associated with the positive charges, is greater than the charge density associated with the minus charges. That means there's going to be now, in this reference frame, there's going to be an electric field coming from this wire because of that difference in spacing, right? And now it looks like a charged wire because there's more positive density than negative density. And this negative charge then, seeing a positively charged wire with a certain specific electric field, is naturally going to be attracted to it and is going to begin to accelerate downwards towards it. He's going to feel a force from that additional set of positive charges. What that means in the laboratory frame, of course, is that this minus charge then, instead of going just straight off at constant velocity Vd, is going to actually want to begin to curve downward and is moving precisely as though he was experiencing some extra additional force in this system. Now, we don't have time to carry out the full analysis of this phenomena, but there will definitely be a downward acceleration. We would have to take into account the imbalance of positive and negative charges, this acceleration that the minus charge feels in his reference frame. We would have to include additional factors because of the time dilation to figure out what the acceleration would be in the original reference frame. There's also a change in the inertial mass of this minus charge. So there's a whole series of extra effects that we don't have time to explain to you in all their detail. But if you were to carry out the full detailed analysis, so for the full analysis, you come to a very interesting conclusion. So this full analysis, of course, you have to do the charge imbalance, like I just said. You have to take that into account. You have to take into account the time dilation. And mass effect. How all those things affect the acceleration. But at the very end of the day, what you will find is that there is now an additional force that we would not have expected. It originates, of course, from this extra electric field that the moving charge sees in his own reference frame. Now, when you work out the mathematics of all this, you'll find that the force, not surprisingly, is proportional to the charge. It's proportional to its velocity in the x direction, right? Because all of those contraction effects all relate, of course, to the velocity. There is a division by c squared. These relativistic effects occur in a couple different locations that give us a c squared. It then is proportional, sensibly enough, to the current flowing through the wire. We then have a denominator that's very intriguing too, because in it you can really see that we are dealing with the formula, right, for the electric field due to a charged wire, right? There's a factor 2 pi r epsilon naught that we usually see from Gauss's law when we deal with a wire. And finally, the direction of this is in the y hat direction, like so. If in this case I were to make a complete coordinate system that then would have coordinates that would go like this. I want to make sure I make a right-hand coordinate system for reasons that you'll see coming up later. So I write it this way so it would have a positive acceleration, but as we saw, the acceleration would have been downward, so the y-axis actually has to have been pointing downward. So this is what we can conclude here directly from relativity. Now, it turns out that this phenomena of these wires actually being attracted to each other due to this length contraction effect was discovered long before people understood relativity. They just observed it as a mysterious force that occurs in the laboratory whenever you have two parallel wires carrying current, that these wires would be attracted to each other with a certain mysterious force. So there was an empirical observation of this originally. So they had no idea what the origin was, and that had something to do with an electric field effect and relativity. How the law was traditionally written down, and this is the way we'll be doing it for the next few units in the course, is they noticed it was proportional to the charge and the velocity, v sub x. It was proportional to the current, of course, and there were additional factors of 2 pi r, and then this would go in the y hat direction. So you have all the key ingredients that were just observed empirically. So this was observed as an empirical fact. And when it was observed empirically, of course, they needed some proportionality constant to put here. So they just gave it a name. They didn't know it had to do with c squared and epsilon naught. They just called it this permeability factor mu naught. But we can see, because we know relativity, a little secret here. Note, and that little secret is that this mu naught is not some new empirical factor from some new physical law. It's actually directly related to the electric field and the speed of light, because this is a relativistic effect. And when you compare the two equations, you see that mu naught actually must have exactly the value 1 over epsilon naught times c squared. Very good. Now, that is for the x direction. Further observations were made about having the particle travel in a series of different directions, and observations were made there as well. So I'd like just to give you the final observations. So the final observations then were that if you were traveling, there's 2 more facts, right? If you travel along the z direction with this additional charge, so what I'm going to have then is a wire consisting of a series of positive charges, right, with minus charges, of course, moving, like so. The minus charges are moving in this direction. So in my wire here, I might have a current I flowing down like that. And if I make my particle move in the z direction, which is inward, right? If I have x and y, and I set up a right-hand coordinate system by the right-hand rule, z would have to be in the inward direction. So if my particle is traveling along the z direction, what I find in that case is that, in fact, if the velocity is in z, the force that I get from this ends up just being 0. So that's interesting. And then finally, I could also imagine myself traveling along the y direction. So if I travel along y, in that case, I would have my wire once again, right, my current I flowing this way. And if you work through the whole analysis, this can either take this as an observation, or also you can see it from relativity, that when I'm moving along z, right, there's no contraction along the other direction, so everything looks kind of normal. When I go along y, things get a little bit more subtle, but if I travel along the y direction, then I find that the force that I end up with then has the following form. It ends up with a minus sign q times the velocity that I have in the y direction times mu naught times the current I divided by 2 pi r. And in this case, the force turns out to be in the x-hat direction. So what we're going to do then is we're going to, in the next lecture, we're going to take these main observations of the force, depending upon which way I'm traveling, that you can either derive these from detailed relativistic derivations, or you can simply take them as an empirical fact, but we're going to bind them together into one physical law and begin to look at the consequences of this type of a force.